Welcome to Analytics Nexus. Thanks for joining us for Gary Angel's presentation, an introduction to Internet of Things analytics. Considered one of the leading customer analytics and digital measurement experts in the world, Gary is the CEO and founder of Digital Mortar. Digital Mortar provides comprehensive collection and measurement of the customer journey in retail stores. Previously, Gary led Ernst & Young's digital analytics practice, helping a variety of Fortune 1000 brands drive digital transformation and performance. Ernst & Young acquired Gary's last venture, Symphonic, in 2013. As president of Symphonic, Gary led their growth from a two-person team to become a leading digital analytics practice in the United States. He podcasts at the Measurement Minute.
Hey everybody, thanks for joining. My name is Gary Angel, and I'm going to be walking through this presentation on the Internet of Things and the particular challenges of analytics that it generates. I'm going to start with a little bit of background. I know there's been a lot of hype about IoT, the Internet of Things, but people may not realize just how ubiquitous these devices are. The numbers are actually pretty staggering. If you look at that upper right-hand chart in terms of the growth of IoT devices, that's billions of units, billions with a B, and that's across a really wide range of industry segments, and it's global. Every country in the world, every region in the world has got significant IoT deployments going on. IoT deployments are continuing apace. You can see that the momentum is pretty serious. A lot of those IoT devices are using cellular connections. They're connected devices, not standalone devices, and that's really important too when it comes to getting data off them and doing analytics. And a lot of people think, and I know that every industry and every analyst has these kinds of predictions. But I think a lot of people are in agreement that IoT is going to be an incredibly important part of the analytics and business landscape in the next few years. So bottom line on this is that IoT is not just a lot of hype. There's a tremendous amount of actual IoT deployment in the world. These devices are everywhere, often shockingly ubiquitous, and they're creating a lot of opportunities for really fascinating analytics. And that's primarily what we're going to talk about today. Just in giving you a little sense about how many different kinds of devices there are, one of the really interesting aspects of IoT is it isn't just one thing. There really are a lot of different kinds of Internet Things devices, and they all present slightly different kinds of challenges. This is actually a temperature sensor. You can see the little thermometer on there. That's nice. This is a motion sensor, right? That's picking up people moving or objects moving in space. This is part of a blue tag mesh network. This is a Wi-Fi sensor. The little antenna is picking up Wi-Fi signals from devices. This is a standard stereoscopic lens video camera for tracking objects and especially people in space. This is a light sensor picking up changes in lighting and what's going on in the environment. This is a moisture sensor used in agriculture. You stick these in the ground and you can measure whether or not you have enough moisture in the ground. And then of course there's the kind of IoT devices that maybe as consumers we're a little more familiar with. IoT devices in things like refrigerators, and of course the ubiquitous Nest device that is a smart thermometer for your home. Literally across this entire range of industrial applications, measurement type applications, security type applications, and consumer type applications, there are IoT devices for almost every measurement purpose out there in the real world. And if there's something that you need to track, chances are there's an IoT device that does that kind of measurement. You might ask, what are these devices really? I mean, these are devices, right? They're electronics. What actually goes inside them? Well, it's kind of a range. And it starts out at the lowest end with those very simple sensors, things like the temperature or light sensors. They're single purpose. They don't really have even a full CPU. They often have some kind of dedicated basic instrumentation in it. There's not really even an operating system in them. It's customized firmware at a very low level. That's the simplest, most basic kind of device. One step up from that is usually a custom board with an IoT OS, so a specialized operating system specifically for low-end IoT type devices. The mid-range kind of device is a custom board running some variant of Linux, often a lightweight Linux variant that's specially tailored for IoT applications. And then as you get up into the more sophisticated devices, you have what are called SBCs, single board computers running full-on Linux variants. These are just like desktop computers. These are relatively robust, usually ARM-based systems that can do anything that a desktop computer can do. And they range in capability from really pretty low-end machines without a heck of a lot of horsepower to machines that are doing advanced machine learning, have GPUs on board, and are really doing serious processing on board. So that's kind of the range of capabilities that you look for in an IoT device. And again, it goes from something that maybe just has a few very basic kinds of circuits and chips on it to a full-on SBC with a GPU on it that can do sophisticated machine learning and real-time processing against data. And IoT encompasses that entire spectrum of devices, which is a pretty large and broad spectrum. But one thing that all these devices have in common, one thing they all do, is they generate data. That's really important from an analytics standpoint. There is an incredible amount of data coming off these devices. Now, that data is sometimes super interesting, sometimes not so interesting, and we'll talk a little bit more about what makes the difference between the two. But at a high level, one of the distinctions that I want to walk you through that I think is pretty important from an analytics perspective as you start thinking about IoT is whether the IoT devices you're using are custom built with measurement as their purpose, or whether data is a byproduct of those devices. It turns out that it makes a pretty significant difference in the types of challenges and the things you'll have to consider as you think about using these devices for analytic purposes. So let's start out with devices where measurement is their purpose. That's things like that moisture sensor, a Wi-Fi sensor, a thermometer, a heat sensor, and a video camera that's used for tracking people in space. That's a device that we use a lot in our company, Digital Mortar. But the idea is that each of these devices has a function, and that function just is measurement. When you've got a measurement dedicated device, there's some things you can pretty reasonably expect to get as an analyst. One is measurement dedicated devices will almost always come with built-in support for a dedicated cloud data store. Hey, these devices are collecting data. Usually they're dedicated to send that data to a specific endpoint or an endpoint you designate in the cloud. That also means that they're usually exposing a full API so that you can get the data that you need. And they often come with at least some pre-built analytics tools. Now, it's true that we usually at least end up ignoring those pre-built analytic tools because they're usually not sophisticated enough or flexible enough to do what they want. But from an out-of-the-box perspective, it's often nice to have a pre-built tool that lets you get your hands on the data and do some basic analysis on it. Okay, that all sounds pretty good, right? I mean, these measurement dedicated devices are doing most of the things that you actually want as an analyst. They're giving you cloud-based access to the data. That's great. So what should you worry about with these things? Well, a lot of times these devices are very basic. Don't have a lot of customizability options. They don't come with a lot of device management. And sometimes security takes a real back seat. The people building these devices think about them from a manufacturing perspective. They think about them being deployed in a controlled environment. They often don't build a lot of security into them, the kind of security that might come standard in a consumer-oriented device. So as you think about measurement dedicated devices, from an analytics perspective, it's great. From a broader device management and deployment and security perspective, as an organization, there's going to be more things to worry about with these kinds of devices. So what about ones where it's like a consumer device and data is a byproduct? You know, if you come out of digital analytics, one thing you'll remember is weblogs. Weblogs are a byproduct of the basic function of a website. And like most byproducts, when a device is dedicated to doing something other than measurement, a lot of times what you have is a polished, reliable device. It's great because from an analytics perspective, hey, people are paying for that device because they want it to do other things. So there's no deployment cost. There's no hardware cost to getting the device out there the way there is with like a moisture sensor or a measurement camera, where the only reason it's going out is measurement. So measurement has to foot the bill for it. On the downside here, though, a lot of times devices like this, because data is just a byproduct, it's not the main focus of what they're doing, you have to worry about getting basic access to that data. Is the device generating a log? Does the log have in it the fields you need? Is the log customizable so that you can get at the things you want? And gosh darn it, this is something to worry about. Will the device actually communicate that data out to the rest of the world? Those are all challenges that a lot of times consumer-based IoT devices that are generating data have not really addressed. And as an analyst, you'll have to think about not just the analytics on the data, but getting access to the data, structuring the data, and making sure that it's communicated to you in a reliable fashion. So really, from an analytics perspective, hey, two big classes of device. One really solves a lot of the analytic problems for you, but may not solve the basic management and security problems. The other is likely to be great for management and security, but may give you a lot of challenges just getting your hands on the data and making sure you can use it effectively. Okay, so now I'm at what I call the big so what, because if you're talking about analytics and IoT and analytics and anything, I think a reasonable question is, well, isn't this just analytics? Is analytics for IoT any different than analytics for customer retention or analytics for digital marketing or analytics for finding oil in wells? Well, the thing about this is that my general answer to that kind of question, and this is not just specific to IoT analytics, is kind of, sort of, maybe. I mean, every area of analytics has its own specific kind of challenges. Yes, analytics is analytics, but when you think about digital analytics, it's a little different than analytics for surveys. And if you think about survey analytics, it's a little different than analytics for employee retention. Different analytic areas tend to have A, different kinds of data, B, because they have different kinds of data and often different goals for using that data, there are often different methods that are highly popular and useful for that particular kind of application. And C, most data sets come with some specific kinds of challenges. And IoT has some unique aspects across all three of those things. Let's start with the data perspective here. So IoT data has some real advantages compared to a lot of other data sources. First of all, it's almost always high volume. It's machine generated. Machines are spinning out this data. And machines don't care. They don't get bored. You can ask the machine to ping out every second, every 30 seconds, every minute. Over time, that's going to generate a massive amount of relatively constant data. Now, one thing you will find with the data generated by most IoT devices is that it's pretty limited. If you're used to dealing with customer analytics and you have a customer database with 100 or 1,000 or 5,000 different columns in it, you're probably going to find IoT data a little bit limiting. A lot of IoT devices spin off a single kind of data. So they'll have a timestamp and a data point. And that might be it. That might be the single kind of data that you get off that device. So you might have data with hundreds of thousands, millions, tens of millions, or hundreds of millions of rows, but only a few columns. That's different if you're used to data that's very rich from a columnar perspective, but very limited from a row perspective. So given that kind of data, well, what are the popular methods? Well, one, virtually all IoT data is time series data. Comes in as a series of timestamps. That's the way the data is generated. That's not always inevitably the case, but it is the case about 95% of the time with IoT devices. So you're getting a steady stream of time series oriented data. What that means is time series methods are extremely important in IoT. Second thing, a lot of IoT applications require anomaly detection. Sometimes that's just what you're looking for. If the machine is generating out statusing and it's got like a temperature detector and every minute it's spinning out a temperature, what you're really looking for is significant variations in this temperature. For the most part, you're going to see 97, 97, 97, 97, 97 over and over and over and over again. And it's the anomalies that are really interesting. It's not always the case, but it's often the case in IoT that anomaly detection is a core part of what you're doing. The second aspect to anomaly detection that's really important is that a lot of times And we'll talk about this in a little bit when we get to challenges, but these are real world devices. There's variation in the environment and the devices. One of the reasons you have to think about anomaly detection in IoT is just to pick up when you have a problem. Not when you have a problem from a data perspective, but when you have a problem from a device perspective. And anomaly detection is really important just for realizing, hey, the data doesn't look the way it should because I have a device offline, or if I have a device malfunctioning, or I have a device behaving erratically. That kind of anomaly detection turns out to be really important for underlying the basic mechanics of analytics in the IoT space. And then the third kind of method that I think is really, really important in IoT is pattern detection. So often what you're looking for in the data is a certain kind of pattern. This is really true in the camera stuff that we do. So we use cameras to track people through physical spaces, and really it's all about patterns in the data. It's looking for the way people move, the paths they go through, the places that they stop and linger. The patterns in the data turn out to be what's really important. So a lot of times you're not looking at, say, traditional correlations in the data. You don't have a bunch of columns where you're doing a factor analysis or a correlation analysis. What you have is a single data point flowing over time, and what you're primarily focused on is finding the way that pattern changes over time. Okay, so that's data and that's methods. Let's talk a little bit about challenges. I think the two big challenges that I've found in dealing with IoT data come from things that ought to be obvious, but as an analyst can really surprise you. One is environment variability, and the other is device dependence. What do I mean by these? Well, these I think are worth drilling down to in a little more detail. So let's talk first about the environment challenge. And I come out of digital analytics, and in digital analytics, everything's virtual. You know, we put tags on a website, the website is deployed, and we start collecting data. And yes, there is an environment. Every once in a while, the data center and the website go down and we lose data. But for the most part, we're working in an entirely virtual environment. We don't have to think about things like light and cold and heat and moisture and dust and people and noise and vibration. But believe me, in the world of IoT, those things matter. They will reach out and grab you, and they will make your life miserable. A couple learnings from this. You know, when you put devices out there in the field, one, the things you tested in the lab will never work right on first deployment. And I have countless stories about this. I think one of the funniest stories from our perspective is, I shouldn't say funny from our perspective, it was miserable from our perspective, but it is kind of funny. When we were first building custom devices for IoT data collection, we were building Wi-Fi and Bluetooth sensors to track people's smartphones. And we'd been burning custom firmware, and we'd been testing in the lab, and we had a set of devices that were ready to go out to a location. And they'd been running in our office seamlessly for like 2 weeks. And as we got ready to ship them, we put the covers on and we gave them a last run through. And within an hour, every single device had failed. We had no idea what was going on. It was like tomorrow was the ship day for these devices. They'd been running for 2 weeks, and as we got them ready for shipping, suddenly every one of them had failed. And what we realized after a little bit of time was that in putting the covers, we'd been running the devices uncovered. When we put the cover on, the devices all overheated. Just that simple. We hadn't built enough ventilation into the casing so that when we put the cover on the device, the CPUs on the devices overheated and the devices all failed. It took us like a couple weeks to sort that out, a couple of painful weeks when we weren't delivering what we were supposed to be delivering. But that gets to the fact that you just can't think of these devices the way we're used to thinking about compute resources. We're used to thinking about compute resources that are parked in safe locations that never change. But when you ship these devices out, what you'll find is all of a sudden they're in a new environment. The lighting is different. If you're doing camera work, believe me, you're going to find that the light changes during the day, and the light is probably nothing like the light that you tested under perfect circumstances in a lab. The devices get cold, the devices get hot. The devices can get moisture, dust collects. People interfere with them. This is one of the most maddening things about IoT devices, but they're out there in real world environments. They'll get touched, they'll get jostled, they get unplugged and picked up. Those are all things that we just never think about in other kinds of analytics. But those things can have a huge impact on the sensors that you deploy. And as any analyst knows, if the sensors you deploy are getting messed around with, your data is getting messed around with. So there's really two implications for this. I've already touched on one, which is that what you build and test will probably not work on first deployment. And that's just something you have to get used to. Getting things out into the field is a critical part of learning in IoT, and it's a step you cannot ignore and that you have to give enough time to as you think about IoT analytics. The second part of this, and I'll touch on more of this as we get into some of the machine learning stuff, but machine learning training is usually developed under ideal conditions, right? We build a calibration set, we build a training set, and we actually go out of our way in most cases to make sure that conditions are perfect. That never holds up in real world conditions. Conditions are never perfect. And those ML training sets that you build oftentimes are the exact reverse of what you actually want. We'll talk about that a little more as we go forward. So that's the environment challenge. The second part of this is the device challenge. You know, these devices are not locked in secure cages with racks of redundant servers, CDNs, and offsite backups. They fail. They fail a lot more than you're probably going to be used to if you've worked on most other kinds of analytics. They fail in all sorts of ways, everything from hard failures with the device flat out not working to some of the more frustrating things where the device has intermittent failures. Maybe it occasionally gets too hot in the environment or too cold in the environment or too moist in the environment. The device fails. One thing we've seen a lot, and this was something we didn't really expect as we started to deploy devices, was that a lot of times data transmission is a significant issue. Again, we all get used to having Ethernet cables plugged into really high-speed Wi-Fi in our offices. Even our cellular networks are pretty good. But when you put these IoT devices out there in the real world, what you'll find is that a lot of times connectivity is a significant issue. So the device may be sitting there and it may be working great, but it may not be able to get you the data you need. And particularly if your models are dependent on real-time data, that's going to be fatal. So as you think about IoT and analytics, just thinking about the fact that these devices are out there, they're going to fail, and that failure could come from anything from absolute device failure to the device just not being able to send you stuff. That's really important to take account of. Okay, last thing I want to talk about before we dive into some of the real issues around analytics in IoT is that, you know, most of the type of analytics that you're going to be doing in IoT is machine learning based. Boy, the data is perfect for that. You know, I talked about the characteristics of IoT data and the size and quantity of the data, the fact that it's repetitive, the fact that it has more to do with patterns than correlations. All of those things play really well for machine learning. So if you're going to be doing machine learning on IoT devices, here's the typical kind of pipeline from a data perspective that you need to think about. You're getting device raw data, that's getting pumped usually to the cloud. One necessary step on that initial stuff is what we call device anomaly detection. Just looking for, do I have problems with particular devices? And that gets into both the environment and the device challenge of things just going wrong on an occasional basis. Before you do a lot of deep analytics, one of the first things you have to do is figure out, do I have missing data? How much of that data is missing? Why is it missing? And what should I do about it? And then you have your traditional model building at the end of this pipeline. Okay, so that's a pretty typical ML pipeline, but I'm going to talk a lot about that device anomaly detection and missing data handling, because I think those are really the unique aspects of how IoT drives analytic challenges. So, you know, given those challenges, how do you build world resilient models, right? I mean, I think for the most part, and going back to what I said earlier about analytics being analytics, when you actually get into the model building part of the analytics, it's not too different than other kinds of machine learning. The real challenges that we found in building good analytics in the IoT space is not so much the pure model building part, but the world resilient part, making it so that our models hold up to the real world challenges that IoT brings to the table. So here are 4 things that I think are really important from a world resilient model building perspective. And the first one is to know what's missing. A good machine learning pipeline really has to include robust detection of a whole bunch of error conditions, because I guarantee you every single one of these things will happen to you, and will happen to you pretty regularly. First one, this is just understanding when an entire location is down. So some of this is maybe a little specific to the way we think about things, but I'll give you a sense of how we deploy units. We're deploying sensors out to buildings, usually stores, to detect people and people movement. So we might have in a single store anywhere from 10 to as many as 50 or even 100 different sensors in that store. So one interesting thing from an analytics perspective is if all those sensors are down, we're getting literally no data from the location. What that says is we don't have a problem with the sensor. We usually have a problem at the centralized part of the store. Maybe the store lost power, maybe the router's down, maybe the power to those sensors is down. But finding that we lost contact with all the sensors in the location tells us that it's not a sensor-specific problem, it's an infrastructure-specific problem. On the other hand, if we've got 30 sensors at a location, but one or more of them aren't giving data, but the others are, that tells us that we still have basic communication, we have the power in place, we have the routing in place, but we're having problems at one sensor, usually one sensor. Sometimes it's more than one sensor. Sometimes sensors are on what's called a run, which is a single cable line. If you see that, for instance, 5 or 6 sensors are down, one thing we'd always want to check is, are they on the same run? Which means that there's a problem just with that cable run. Everything else might be up and working. Those are pretty straightforward, right? You're either getting data from a sensor or you're not. This next one is trickier. Partial data from one or more sensors can easily slip through the cracks. So in other words, you have a sensor, maybe it's up for 22 hours during the day, but it was down for 2 hours during the day. If you don't find that kind of condition in your pipeline, what will happen is the data you feed into your models will be significantly broken for that 2-hour period. That's really easy to miss. So often data is getting aggregated up to higher levels. And if you have partial data from a sensor, it's really easy for the conclusions from the model to be skewed without anybody ever recognizing why. So one of the most important things to look at to building a world resilient model from an IoT perspective is making sure that you are constantly tracking whether a device is heart beating, whether it's sending the data it's supposed to be sending, and whether it did that constantly throughout the day. And then lastly, of course, there's the problem of anomalous data from one or more sensors. What if a sensor traditionally picks up, say, 100 people in a particular location in a particular day, but now it's picking up 5,000 people, or it's picking up one person? Okay. Sometimes that might be an issue. Sometimes that's not an issue. If it's a university and it's closed for that day and it's holiday, you may not expect to see anybody. If it's Black Friday, you may expect to see a dramatic jump in the number of people in a location. But identifying those potential anomalies are really important. In terms of people detection with things like cameras, we've had everything from inserting a mannequin into an area where all of a sudden the camera now detects that mannequin as a person over and over and over and over again, to changes to the area, to people blocking the camera. So people putting an object or a display right in front of the camera, so the person count goes from something normal down to 0 or 1. Lots of stuff can happen out there in the real world, and being able to look not just for partial data, but for truly anomalous data. So the device is heart beating, but it's giving results that are suddenly significantly different than it's ever given before. All of those things are really important. If you let that data flow through into your models, a lot of times the models will aggregate the detail out and they'll give you conclusions, and those conclusions may not be obviously erroneous in a way that the raw data is. So a really robust set of routines for figuring out what's missing in the ML pipeline is one of the most critical things in doing IoT analytics. Which brings me to, I think, the second big challenge: ponder missing values. If you have device anomalies, if you have device failures, if you have partial data from devices, one of the things that's going to generate is missing values. Missing values are a plague on machine learning analytics. A lot of times we tend to think of missing values as something we can just throw away and ignore, but those missing values can have a huge impact on model results. So once you've detected those missing values, you really have to think about, in my machine learning pipeline, what do I do with them? And here's the sort of set of ranges, the sort of set of actions that you can think about doing, starting with my old favorite, do nothing. Yeah, you can do nothing, but doing nothing about missing values is probably going to guarantee that those missing values are really mucking up your models. Second thing you can do is just say, hey, I'm going to code them as missing, and I'm going to let the model handle it. The problem with that is that a lot of models handle missing values just by throwing away the rows. That is really not ideal in a lot of cases. Third technique is when you get a missing value off a device, just to substitute the average from the device. It's a really brute force method. Occasionally, it works. It can work with certain kinds of anomaly detection, but in most cases, that's a bad strategy. The next kind of method is substituting a simple prediction. So in other words, if I have a missing value, I'm going to do a simple prediction using the other row values, and I'm going to try to put a value in that place. And then there's a technique called multiple imputation. There's a whole set of new statistical methods that are designed to impute missing values on a kind of multi-regressive basis. That's the most sophisticated way to treat missing values. It's almost certainly, in most cases, the right way to treat missing values in a machine learning IoT problem. So then there's three other things that I want to hammer home about missing values. Each of these may be a little bit unclear if you haven't struggled with missing values, but all of them are worth learning about. The first one is that imputation is better than deletion. What do I mean? Well, I really just talked about this. Don't just throw away rows with missing values. The missing values are often super significant from some standpoint in the overall IoT system. Imputing values will give you better models and better predictions over time. So don't throw away data, impute data. Amputation, which sounds like the reverse. It is kind of the reverse of imputation. But a lot of times when people build models, one of the things they'll do is amputate data. They'll get rid of certain kinds of data as they train to try and simulate what's going to happen with missing values. One of the keys to thinking about amputation when you build training sets is that missingness is usually at the device level, not the variable level. What do I mean by that? Well, if you have a sensor and that sensor is collecting 4 different kinds of signals, what you may find is that occasionally one of those signals may be missing, but the more common case is that all 4 of the signals from a single sensor are going to be missing. That's really important because if you are simulating missing values in a training set and what you're doing is just turning off one value at a time, you may not capture the kind of missingness that often happens in the real IoT world, which is the device goes down and all the signals from that device are missing. That's why I say amputation. When you think about amputation, don't think about it at a single variable level. Think about it as it commonly is at a device level. And then this last one uses some acronyms here. MAR versus MNAR, it does matter. What's at stake here? Well, a lot of times when we think about missing values, our implicit assumption is that the values are randomly missing. MAR stands for missing at random. Okay, so that means that it just happened that the device is that you're missing a signal from a sensor. It doesn't have any particular significance. That's sometimes true, but you can't count on that. A lot of times in real world situations, a missing value is super significant for interpreting meaning out of the system. What that means is that a lot of times in IoT, you're faced with an MNAR solution, a missing not at random. And so when you create training models that are designed to capture that kind of data, you can't just randomly drop values. You have to think about what kinds of patterns of values are actually going to be missing and what that might mean. Missing not at random is a much harder kind of missing value substitution that you have to deal with. The thing is, it's the kind of missing values that we see most often in the IoT world. So I just want to stop on this slide and hammer home this point. Missing values are something that a lot of times in a lot of traditional analysis, we don't spend a lot of time thinking about. We just throw them away. And that works for certain kinds of analysis, but in the IoT world, handling missing values is one of the most important things you can do in your analytics process and in your machine learning pipeline. Okay, this brings me to something that I think is every bit as important as handling missing values, and that's to rethink the way you do machine learning training. And this is very much from personal experience. And this first bullet point is something that I can hardly overstate. Every analyst I've ever met, and God knows I feel this way too, when you're building machine learning models, you keep tweaking them and tweaking them and tweaking them. There's an irresistible urge to maximize model prediction and training, right? You just keep adding variables, you tweak the variables, you tweak the model. It's really rewarding and fascinating to go through that process. There's constant feedback. Every time you tweak the model, you run it, you get to see the prediction accuracy. When the prediction accuracy goes up, it's super gratifying. And what that means is that as analysts, we spend a lot of time in the process just trying to get that last few little increments of accuracy out of the model to get from 87.8% to 88.3% prediction accuracy. Stop. I can't say anything else, but in the IoT world, stop doing that. There are times when that might be appropriate, but I think what we've seen in the IoT world is that focusing on that absolute maximization of model prediction and training is not just a waste of time, it's actually a flat out negative. The reason is that there's so much variability in training and conditions and real world variability that almost everything you do to maximize model prediction and training, when you get to those small incremental tweaks, will make your models less simple, less robust, and less consistent when you actually deploy them in the real world. So some things to really, really focus on from an IoT training perspective: simplicity. Boy, don't just throw variables in that give you very small incremental gains in prediction accuracy. They will bite you when you deploy these models in the real world. The fewer the variables, the higher reliability you'll have in the model, the less dependency you have, the more your models are going to hold up in the real world when you deploy them. The second thing is, and I've already touched upon this a little bit with missing values, but this is critically important: do not go out of your way to optimize the training conditions that you work under. When we started doing IoT models, we tried to build calibration and training models that really focused on ideal conditions, every sensor being active, the store being empty, everything being perfect from a measurement perspective. That is not the right way to do it. Your training models, your training data has to reflect real world conditions. What that means is your training data needs to capture conditions when sensors are down. It needs to capture conditions when lighting is poor, when the temperature is high, or when the temperature is low. Whatever can affect the training of your model, that needs to be implicit in the training data sets that you collect. People do not think about this right. The demand to try to get perfection in idealized training data is the worst mistake you can make in building machine learning models. That really gets to this third one: consistency. Create bad condition training sets. Do this explicitly. Don't try to make the calibration perfect. Don't try to make the training data perfect. That is not what you're going to have in the real world. And if that's what you have in your training sets, you're never going to be able to build models that are reliable and robust enough to handle real world conditions. All right, last point I have about world resistant models, and I've already talked a little bit about this, but I want to highlight some of the techniques we use because I think they're really interesting and worth knowing. I call this modeling for failure. So to give you a little sense of what I mean here, think about a location. So you've got a building, and we deploy a bunch of sensors to track people through the building. So if you look at the planogram, you can see this is the outline of a space. Each of those blue dots is a sensor deployed. The way this works is that we pick up signals from devices on multiple sensors, and then we triangulate and use machine learning to, based on the strength of the signal received at multiple sensors, position the device inside the building. Okay, so this is geolocation tracking based upon signal strengths received at multiple devices. Here's the thing: when we build models for this, and we have a device, and the device circulates across the location, constantly pinging out, so the devices are picking it up. We know the location of the device, we know the signal strength at all the sensors, and we can build a really robust model that can geolocate a device down to with really high accuracy to its position on the floor. Make sense? Okay, here's the thing. In the real world, what happens if one of these devices goes bad? Well, think about it. What we're looking at is the signal strength on devices. And when a sensor didn't pick up a signal strength, usually that means that the signal was quite far away from the device, too far away for it to pick up a signal. That's the way the model assumes what's happening. So if this sensor didn't pick up a signal and this sensor did, the model is going to assume that the device was somewhere further away from the sensor that didn't pick up the signal and closer to the one that did. So it's going to geolocate that signal. But what if that's just a missing value? What if that sensor was down? What's going to happen is suddenly all the device positions are going to shift away from that signal because the model doesn't recognize the difference between the sensor not picking up a signal because the emitting device was too far away and the sensor being down. So one of the things that we do to try to tackle this problem is in that machine learning pipeline, we track which sensors are actually picking up signals at any given time, and then we use a configuration of sensors as available. So we basically build models for all the possible different configurations of sensors that are live. So we know if this sensor is down, we're going to deploy a model that doesn't use this sensor and so doesn't implicitly shift all the signals. That's really complicated. It makes for a much more complicated machine learning pipeline, but it was what we had to do to handle a situation where data frequently in the real world is just missing. So model for failure is one of the most important things that I can emphasize about doing IoT analytics right. Okay, that's the presentation. What I'm going to do now is just sum up what I think are the key takeaways from this whole long digression into IoT analytics and how it works. I'm going to start with the basics. IoT is not just hype cycle. There are tremendous numbers of IoT devices in production and available. A lot of those IoT devices are measurement dedicated. When they are measurement dedicated, it makes it really easy on you from an analytics perspective. They almost always give you clean, easy access to the data. When they're not measurement dedicated, one of the things you'll have to worry about is just, can I get the data off the device, and can I get the data that I want off the device in a manner that makes it usable? Like anything else, IoT analytics isn't a completely unique kind of analytics. A lot of the things you know about doing analytics on any other kind of field are going to apply. But it's also true that, like most other analytics fields, it's distinguished by the data and methods that are peculiar to it. And part of that is that it's very highly appropriate to machine learning. It's machine generated data. It's usually high volume. It's time and pattern oriented. That makes it just about perfect from a machine learning perspective. The two biggest challenges in doing IoT analytics aren't where I think most people would project them to be, but from my perspective, they come from the very nature of doing Internet of Things analytics, environment variation, and device issues. And if your experience is anything like mine as you do IoT, you're going to find that both of these things make life really, really challenging from an analytics perspective. How do you handle those two things? Well, the four things that I talked about from an IoT analytics perspective are all really about building world resilient models, models that hold up under different environments and hold up under device failure. And the first thing that I really want to emphasize is it starts with knowing what's broken and what's not working. A key part of a good machine learning pipeline is careful heart beating, tracking statuses of IoT devices, knowing what's available, knowing what isn't, and then adapting your machine learning modeling based on that. Second thing, have a coherent, reasonable, tested strategy for handling missing data. Missing data will happen. It can be incredibly important. How you handle it can make the difference between a robust model that functions really well in the world and a model that is constantly breaking and giving people misleading and poor answers. Third thing, rethink your training strategies and stop over focusing on getting the absolute best prediction value. because of the variability and challenges of devices in the real world, the simpler you make your models, the more robust and consistent they will be. Use fewer variables, give up on absolute maximization of predictive value. I think you'll find that that produces a better IoT analytics system in the long run. And finally, build a machine learning pipeline that allows you to adapt the models you're using based on current real-world conditions and real-world device availability. This is hard, it's complex, it makes for a much more complex, in some cases, a much less performant machine learning pipeline. But in general, what we found is that it makes a huge difference in the quality of analytics and the consistency of the model outputs that you get from IoT. That's the presentation. I hope that A, you're interested in thinking about IoT analytics. B, I hope if you're getting into IoT analytics, that I've given you some real food for thought about where the real challenges and difficulties are in IoT. I hope in this coming year you get a chance to really explore this kind of analytics and take advantage of some of what you've learned today. Thanks a lot. I'm Gary Angel, saying thank you.
Thanks so much for watching this presentation. Join us on the Analytics Nexus Slack to talk with our presenters about this topic and more.